You've started working on your homework problems assigned out of Chapter 8. And what I want to do is take you through a set of 4 videos to show you the fundamental governing equations for each of the 4 components of the Rankine cycle. I'm going to start with the boiler and then move on to the turbine, condenser, and feed water pump. So I'm going to start with boiler basics on this video. However, in your homework problem solving process, you are probably going to start at the turbine. But what I want to do is have separate videos for each component, and then you can pick and choose what you want to watch if you get hung up on one of these components. The trickiest component might be the feed water pump, but let's start with the boiler. So just as a reminder, here's our basic Rankine cycle, and we're going to talk about this boiler process. And I see on the sketch, it's going to be process 4 to 1. And I see there's some heat transfer involved. Let's see, on our basic TS diagram, okay, for a Rankine cycle that has irreversibilities. So where's our boiler process going to be? It's going to, for an irreversible pump, it's going to start at 4A. That'll be like 4. We'll call it 4. And we're going to come at constant pressure, heating until we get to state 1. And there we're going to go into the turbine inlet. So it's this process here that we're going to analyze. Okay, what does that look like from a real piece of equipment standpoint? Well, let's see. State 4, this is going to be our feed water in coming from the pump. It goes through all kind of gyrations that you don't even really have to even worry about. What you do have to worry about is it's coming out as superheated vapor to the turbine. Maybe in starter problems, it'll be saturated vapor, but in the real world, it's going to be superheated vapor to the turbine. And then recognize, of course, that the combination of fuel and air and resulting combustion is your high temperature heat source. And so you've got heat being added to this steady state, steady flow, one inlet, one outlet situation in the amount of Q dot H. Okay, so similarly with the package boiler, gas-fired boiler, same idea. We've got state 4 coming in, feed water in, and state 1, superheated vapor going to the steam turbine. Same idea with the natural gas in and air, high temperature heat source with Q dot H going in, of course. Well, what would your sketch like? So here's what I suggest your sketch should look like. I'd show a high temperature heat reservoir, TH, sort of a big sloppy arrow, Q dot H going in to sort of this black box, one inlet, state 4, outlet state 1, going to the steam turbine. And look, for your purposes, I think just showing some kind of little squiggly line showing that heat is being transferred into this squiggly line heat exchanger, that's good enough. Now, fundamentals. What are our fundamentals instead of just plopping down a formula? Open system, steady state, steady flow. Well, steady state, m.4 equals m.1. Well, let's just call that m dot. We don't need to call it m.1 equals m.4. M dot. One inlet, one outlet. There can be exceptions for reheating the steam. We're not going to worry about that right now. Okay. Another important thing to recognize is that P1 equals P4. This is a constant pressure process. Do you see a weight being lifted in your sketch? Do you see a shaft coming out? No. W dot out equals 0 for the steam generating unit, for the boiler. That's key. We'll apply the first law. That's a fundamental. That's not a formula. Okay, Q dot in minus W dot out equals M dot times H1 minus H4 out minus N. And of course, I don't even think I wrote it down anywhere, is that we're neglecting changes in kinetic and potential energy, of course. Okay. That's a key. Okay. And you say, oh, I've got that. I got my units right. I don't, this is a dumb video. In your textbook, you're going to see that in many cases, they divide this fundamental first law by m dot, divide both sides by m dot, and they get little qn, q dot over m dot, that's little qn, simply equals h1 minus h4. So please recognize that these two formulas, they're identical statements. They're not special formulas. They're identical statements of the first law. So the reason the textbook does that is that in analysis for systems operating in a cycle, it's common to not be provided with m dot. So don't let that be a barrier to you in your homework solving. Is recognize that in the textbook, they come up with little qn equals h1 minus h4 by dividing by m dot, and in many cases, m dot is not a given number. All right. Okay, and so if you want to see those types of details worked out, just go to my homework solutions playlist, find problem 816. Although it does run 51 minutes, you could pick and choose maybe where you're getting stuck with your particular problem. Okay, I hope that helps. Next video is going to be turbine analysis.